Okay, how to read your Synchron motors. We're going to be going across this chart here, just telling what each indicator means. So I'm going to go over this slide real briefly here. But the first example is an A12RA, and that's a very common motor actually. So we're just going to use that same A12RA numbering sequence as we go along through here and maybe talk to you a little bit about what each one of those characters means. In this picture, there's also on the right-hand side a round motor with a part number 38080L. That is what we would call an OEM number. The OEM number it means it was a motor that was manufactured for a special application, and it went to a company who built a product around it. So the L in that part number designates that it's a left-hand motor as you're looking at the output shaft. We'll get into that a little bit more. What we're going to focus on is the motor on the left, the BB12LC type of motor. So when you see a number such as that, a BB12LC, so you got letters, numbers, letters, and some dash numbers, those are more of a generic type number, and that's what we're going to be going over in the slides to come. So with that, I'll move forward to the next slide. The first letter in the generic part number is an A, and the A can mean many different things. It can lead or mean things like lead length, how long they strip the wires, the position where the leads are coming out of, possibly the color, the torque rating of the motor. I'm not saying it's not important, but I think there's more critical things to come that are more important when matching a motor. So with that being said, if you have a motor that everything matches on it perfectly except for that first letter, chances are that motor is going to work for you. It might be a different color wire or something similar to that, but if everything else matches on the motor, I wouldn't worry too much about that because it just might be the wire coming out of a different area or different color or things such as that. So the next one, which is the 12, is obviously really important because it is the output of the motor. The pinion, gear, shaft, whatever you prefer to call it, but they do have to be matched up for your application. So for instance, a 12 shaft, a 13, and a 14 are going to look like the motor down in the lower left-hand corner with the red and white wires. The difference between a 12, 13, and 14 is truly just the length of the shaft, how long they come out. So in some cases, you might be able to substitute a longer or shorter shaft for the one you currently have. The other thing about the number is, if you look at the top picture, one of them, and you can't really see it, but the one with the brass gear up on the top left-hand corner is actually a number 43 pinion. And to the right of that is a number 44 pinion. Now, you really can't see in the picture that they're the same size. I know that they are the same size, but the distinguishing factor is the color of them. So the real difference between those two pinions is just the material they're made out of. One is brass, one is steel. So again, they can be substituted for each other as long as everything else matches on it. So the next character, one thing I want to say about these here before I continue on is the number 12, 13, and 14 shafts. So the motor in the lower left-hand corner, sometimes they do have a flat on one side of them. And the flat actually allows for a set screw to go in and hold a cam or some type of gear that might be installed on that for a different application. So again, sometimes a flat or just a round shaft without a flat can be substituted. And it's not critical. So let me continue on to the next one. Next one is fairly self-explanatory. As we're looking at the gear or the pinion or the shaft, however you want to define it, it's just a rotation of the motor. So however, if it turns right or clockwise, it will have an L in this character. Left would be an L for counterclockwise. And so L would be, I'm sorry about that, L would be for counterclockwise. So depending on how you're looking at the gear, what direction it turns is going to signify whether it's an L in this position or an R in this position. Usually that makes a difference as far as clocks go. There are, I guess, some applications where it doesn't matter which way it goes, as in if it's moving a animation or something like that for a display. Continue on to the next slide, which is 3 different pictures here. And really what it represents is the mounting of the 3 different motors. So as you can see, the motor on the left has 4 what we would call mounting ears or tabs. The middle one has 2, and the right one has 2. As we're looking at these, one thing I do want to mention is the one on the right. We also, when we're talking to people, call that a pair or teardrop shaped motor, because it does have a distinguishing characteristics of how it looks. The other 2 are certainly round motors, and then they can be identified with 2 or 4 mounting lugs. But the character here, so the motor on the left is an A, and it would have the 4 mounting lugs. The motor in the middle is actually what they would signify as a D mount. And the motor all the way to the right is signified as either a C or a K mount. Typically in our clients' applications, we would probably see the C mount, but you might run into some K mounts in chart recorders and things like that. So I'm going to continue on to the next slide, which is really what we call the dash numbers. This picture right here would be a -5, -6, which means that it has a little window there. And that little window on the cap of that motor actually lets you see the rotor in it turn. So you know that just by looking at the motor from this angle that power is applied to it and the motor is turning. That would be a -5, -6 on the motor. Another one would be a -76, and a -76 means it left the factory, the Hansen Synchron factory, mounted on a gear train or mounted on a movement, not just sold as a motor. So again, as you can see, the dash numbers sometimes are very important, sometimes are not so important. One last thing that would be very important would be a -1W, which would be a one-way clutch on it. And that clutch can either go to the left or right, 1WL, 1WR. What the clutch is for is in certain applications where you might have 2 motors controlling a gear train. The motor has to have a clutch in it internally in order to have some give to it, so the gears can spin when one motor is turned on versus when the other motor is turned on. So you might have a normal drive motor that's running 99% of the time and a speed up or catch up motor that's only turned on occasionally. If those 2 motors didn't have a clutch in between them, so you have a motor on one side, you have gears, and you have a motor on the other side, if there was not that clutch in between it, it would lock up the gear train trying to turn the other motor. So that's why it just has to have that clutch or give in there. With that stated, we'll go to the next one, which is voltage, speed, other information. As you can see on the description here, it does say 110V, 60Hz, 4 watt, 1.5 RPM on this example. Other voltages that we deal with would be 24 volt, and we deal some with 220 volt, which would be mostly for overseas. Hansen or Synchron claims that their motors run plus or minus 10% of the nominal voltage. So if the motor is stamped 120, obviously it can work on 110 and such. The other important factor on here is the hertz. 60 hertz versus 50 hertz is the other option. If you do have the wrong hertz, the motor is going to either run fast or slow, depending on which way the hertz are wrong. So hertz are important for the speed of the motor, but it's not important as far as functionality goes. I mean, it'll work on either hertz without any damage, but in order to work properly, it does have to have the right hertz. The other important feature here is a 4 watt. Typically, our motors that we deal with are either a 3 watt, a 4 watt, or a 5 watt. A 3-watt motor gets warm to the touch, where a 4-watt motor gets, I'm going to say, hot. I mean, you can hold your hand on it for a little bit, but you won't want to hold it on there for a real long time. A 5-watt motor, it'll actually almost burn you. So even though it's only 1 or 2 watt differences between the motors, it does make a big difference as far as the heat of the motor. If you go up in wattage, you also go up in torque or power output. So that's one benefit to going up in wattage. But in our clock world, so to speak, we are usually at the 3 or 4 watts. Sometimes we use a 5 watt when it's a dual motor application. The other thing that we see on here, I don't have any real, there is an example of it, is the date stamping, which is on the right-hand side of the motor. I'm sorry, it's on the motor to the right. 0333. So what that means is that motor was built in 2003 in the 33rd week. So it was built in 03 in the 33rd week of 03. The other way of identifying motors' dates, they use a more traditional way prior to this. I don't know when they changed, but they would use something like 10 of 97, which would be October of 97. So there's 2 different ways the motor could read. The older motors read month and year. The newer generation reads year and week. With that said, I believe I'll go, I forgot to mention the RPM, RPH, RPD. So I think it's really important to look at the RPM. The one motor pictured here is 1.5 RPM, revolutions per minute, revolutions per hour, or revolutions per day. We have also seen revolutions per week, and I'm sure there's others out there that, that I can't think of at this point. One thing you have to be concerned about, or at least aware of, is fractions. So you might have a motor that reads 1/24 RPH. 1/24 RPH is equal to 1 revolution per day. Another one would be 1 RPM is also equal to 60 revolutions in an hour. So just because the RPH does not match identically to what you have doesn't mean that it might not be, you might be able to use it. So check for fractions, or make sure that once you break it down into to get down to the RPMs or the speed you need. I'll advance to the next slide here. This is one of the things I think it's going to be pretty exciting for the future. I know a lot of you have probably dealt with the old traditional mechanical movements that have been used really for decades in various manufacturers' clocks. They're still used today. We build plenty of clocks with that mechanical movement. So we're going to be going over that briefly, hopefully in a future upcoming webinar. Another one that we're going to be touching on is the solid state movement, which is in the middle. The solid state movement, in conjunction with the circuit board off to the right, is a direct replacement for the mechanical movement that you see on the left. Typically, in most cases, it does come at less expensive and with a better warranty. So there are some benefits to it, but we're going to be touching base on both the benefits and the advantages of both of these here in an upcoming webinar. So stay tuned for that. That should be a good one, and hopefully we won't keep you waiting as long as the next time around. So appreciate your patience again. I want to thank you for joining us today. I really appreciate it. Sorry for the delay. We're learning on this here, so it's going to get better as we go along. It looked like we had a great attendance today, so we're really excited about that. If you have any ideas for future blogs, please copy and paste that address and email us either at marketing@atsclock.com, or you can subscribe to our blogs. But if you have any ideas for new webinars, we'd certainly love to be able to hear from them. I mean, we have our own ideas, but we'd like to know what you guys would like to learn too. So again, I'm going to leave the screen up here for a little bit so you can email us or subscribe to our future blogs, but we truly appreciate everybody that's joined us, and hope you got something from us. Thank you.